So, all right, so like this one, and there is another way of writing this one. So this block, all the way this the left two rows, the left two column, we call them as a S block element. S block, S block, BLOCK block. So if somebody asks you what are the S block elements, so anything from 1A and 2A are S block elements. So why they call S block, I will talk in future class. Yeah. And then all these one, 3A, 4A, 5A, 6A, 7A, 8A, all these elements here, this block is called the P block, P block element. Everything here, all the way, these are called the P block element. And these two column are called the S block element. And in between this one are here. So these elements are called D block element. These are called D block. Any element you pick from this group is called the D block element. And if you look at the periodic table, and at the bottom there are two rows, and these are called the F block element. F block element. Make sense? So it's easy. So I'll put in a homework. So you just look the periodic table and pick the number what you want to pick. Yeah. So these all are blue in that periodic table. These are metals. These all are blue. These are metals. These all are blue. These are metals. And there are some blues here. They are also metal. And those brown boxes up here are non-metal. And there are some green boxes with these elements. They are the metalloid. Yeah. So metal means they conduct the electricity. Non-metal means they don't conduct the electricity. And metalloid means they conduct the electricity somehow. Not as good as metal, not as bad as non-metal. So they conduct the electricity a little bit. Like in our computer, they have the silicon, germanium chips. So they conduct the electricity, but they are not as good as the iron, copper. Yeah. So these elements also conduct electricity, but they don't conduct electricity as good as metal. So they are called the metalloids. Make sense? Good? All right. So this is very important. So we will be coming to this periodic table pretty much every class. Yeah. So remember that these two are S block. These middle elements are D block. These are P block. These down are S. So, all right. So I wrote this note at the end of that periodic table. You can read by yourself. All right. So. In this periodic table, you will see something like there is a. If you look at the middle of the periodic table, you see like the U here. There is a U. It's a U, and then it writes 92 here, 92 here, and at the bottom it writes 238. 38. So we'll study in chapter 2 this one. So what does this mean? So 238. So this element is the U is for uranium. So this is uranium. So if somebody write like this, sodium. Let's say this is Na is sodium. Then all the names are written in the small letter there in the periodic table. You can read those names. Yeah. If there is Na means sodium. All right. Sodium. So you might see something like this. This is 11 here, and this is 23 here. So what does this mean? So Na means sodium. This element is sodium. And what does this mean? So the atom has at the center. So the atom look like this. So at the center, atom has a proton and neutron. At the center, they have proton, 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 and neutrons. So this means this is the number of proton it has here. So there are 11 proton. 11 proton. It means that in this sodium there are 11 proton. Yeah. So we'll talk about the proton, neutron, and electron in next class. So what does this mean? This means there are 11 proton with the sodium. So this atom is a sodium. And this means, so you subtract from here to here, 23 minus the 11, and you get how much? So that is 2 and then 1, so 12. So it has 12 proton, 12 neutron. 12 neutrons. So that means that. Make sense? So this, so whatever you see in the small number is number of proton, and the big number is proton plus the neutron. So this big number here is number of proton plus the number of neutron, and this small number is number of proton. And when you subtract from the big number, the small number here, you will get the number of neutrons. So in this one, you can easily see there are small number is 11 here, 11 is number of proton. So the big number is 23, 23 minus 11 is the number of neutrons. Make sense? So that means that. Now, how about here? So this element is uranium. So uranium is kind of they used to make the nuclear bomb and nuclear energy, those kind of things. So this is a uranium. So how many protons are here? So uranium is very, very big atom. So at the center of that uranium atom, there are 92 protons. We'll talk about what proton, what neutron means, and then how many neutrons are here. So this is small number. Small number is always proton, and then the big number minus the small number gives the neutron. Yeah. So 238 minus the 92 gives you the number of protons. So there are 6, 4, and 1. 146. So this is 146 is neutron. So that means that. Make sense? Good. So a small number is proton, the bigger number is proton plus neutron, and from proton plus neutron, if you subtract that small number, you get the number of neutron. Very important, yeah? So we'll talk in the another class. And this number also shows the number of electrons. So in atom, there are proton, PROTO and proton, there are neutron, and there are electrons. So these three things are in the atom. So the number of protons and number of electrons are always equal. So these two are equal, neutron is different, yeah? So how many electrons are in uranium? There are 92 electrons. How many protons are there? There are 92 protons. So how many electrons with sodium? There are 11. How many protons are there? 11 protons. How many electrons are there? There are 11 electrons. Number of proton and number of electrons are always equal in an atom. Make sense? So that means that. So very important. Good. So you might see something like 238 point if you look the periodic table, there is 238.0, 238.02289. So at this moment, don't look those number after the decimal. Just look the big number there. Yeah. So there is a meaning why there's those small decimal there. We will talk in future, but just look this one. So this is a proton plus neutron. This is a proton, and this is a proton as well as electron. So number of proton and number of electron are equal. So this is 92 proton. This is neutron plus proton. Good. All right. So we studied the very important concept. So all right. So now we talk about the mole concept. So these are very, very important in chemistry. Yeah. So what is the mole? Mole concept. So mole. So look at the periodic table. So if you are there with the periodic table, now let's talk about the lithium. So I go to the first row, and I pick the second element. So lithium. There is lithium, right? So Li is lithium. And you write the small number there is 6.9, right? If you look at periodic table, there is 6.941. So it writes 6.941. So it means that, so this is approximately 7. So 6.941 is approximately 7, right? So 7. So you can write 6.941 or you can write 7. So this is the mass of the lithium. This is the mass. If you take the one atom of the lithium, the scientists give it, so the mass number is 7. Yeah. So hydrogen is 1, lithium is 7. So how heavy lithium compared to hydrogen? If you give the hydrogen mass 1, so lithium is 7 times heavier than the hydrogen, right? So now what is the mole? So look this number there. Let's say 6.941 4 1 is 7. I put the 7 there. So if you measure 7 gram in laboratory, then you measure 1 mole of lithium. Make sense? So what is the number here? Go to the laboratory and measure that much mass in gram, and that is 1 mole mass. Make sense? So another one is, let's talk the beryllium. So in beryllium there is 9. So beryllium is 9. So beryllium, if you see here, at the foot there is 9. So go to the laboratory and measure 9 grams. So you measure 1 mole of beryllium. Yeah. So how much is this mass? That many gram is called 1 mole. Yeah. Good. Now let's talk about the water. So water. So water is this one. So water molecule is H2O. We will talk about this one molecular formula. Water is H2O. Now how many hydrogen are here? So this is 1 hydrogen. There are 2 hydrogen. So 2 hydrogen, right? H2 means 2 hydrogen, right? And there is 1 oxygen. Now go and look the periodic table. So in hydrogen you will see 1. So look that box number 1, and there is 1, right? So hydrogen is 1. And so this hydrogen is also 1. Now look the oxygen. So what is the oxygen? So this is all the way to 6th group in the P block side, and there is 16. So this is 16. I'm not taking those small decimal. I'm just we got a rounded number here, right? So how much is this one? Now add all those. So what is the mass? 16, 17, 18. So 18. So this one is, water has 18 mass. 18. This is called the molecular weight or molecular mass. So we have 18. So if you go to the laboratory and measure 18 gram of water, then you measure the 1 mole of water. Make sense? So you need to calculate the mass from the periodic table and go to the laboratory, and you need to measure equal to that number in gram, not kilogram, not pound, in gram. Yeah. Good. So 18 gram of water is called 1 mole of water. 1 mole of water. 18 gram of water is called 1 mole of water. Make sense? Very important. Now let's look another one. I think I have there carbon dioxide in the slide 3. I have the hydrogen is 2. I already talked about. Now let's talk about the carbon dioxide. So carbon dioxide. So there is a carbon and there are 2 oxygen. So look the periodic table. What is a carbon? So carbon is, I think there is a 12. So look that periodic table. I posted there, and there is clearly right, the bigger number is 12, right? Carbon. If you see there is a carbon is 12, right? Yeah. Look the periodic table, and then how many oxygen are there? There are 2 oxygen. 1 oxygen here, another oxygen here. Oxygen 2 oxygen. So look the oxygen. How much is the mass of oxygen there? So the oxygen is 15.9 is 16, right? So 15.9, I'm going to write 16, yeah? So 16. So 1 oxygen is 16, another oxygen is 16. So I'm going to add this number here, and this is 30 to 44. So add this number and you get the 44. The mass in carbon dioxide is 44. Now go to the laboratory and measure 44 gram of carbon dioxide. That means you measure 1 mole of carbon dioxide. Make sense? Easy? It's very important. Yeah. So 44. So 44 gram of carbon dioxide is equals to 1 gram of 1 mole of carbon dioxide. 1 mole of carbon dioxide. 1 mole of carbon dioxide. Yeah. Good. So like this. So, and you can do all other. You can practice yourself. So what else I have here? Now let's talk about one oxygen, O2, oxygen. So this is the oxygen molecule, oxygen gas, right? So what is the how many gram is equal to 1 mole in case of oxygen? So look the oxygen and oxygen. There are 2 oxygens. So this is 1 oxygen. There means there are 2 oxygens. So I have oxygen and oxygen, 2 oxygen. So look that periodic table. Clearly that bigger number is 16 there, right? So this is I think in oxygen is in group 16 or 6A, so look there, so the bigger number is 16, and another is also 16. Now add these two numbers, so that is 32, right? So 32. So the mass of this O2 is 32. So I go to the laboratory and I measure the 32 gram in balance, 32 gram of oxygen, meaning that if I measure the 32 gram of oxygen in the balance, it means that I measure 1 mole of oxygen. Yeah? Make sense? Good. So this is 1 mole of oxygen. So if somebody asks you measure the 1 mole of water, you are going to measure the 18 gram in balance, right? If somebody asks you measure 1 mole of oxygen, you are going to measure 32 gram of the oxygen in balance. If somebody asks you measure 1 mole of the carbon dioxide, you are going to measure 44 gram of carbon dioxide. If somebody asks you measure 1 mole of hydrogen gas, you are going to measure the 2 gram of hydrogen gas, right? Because hydrogen is 2. Make sense? So that's how we calculate the moles. Now, now I'm in the slide number 4. So I just finished the slide 3. Let's talk about slide 4. So classification of matter. So classification of matter. So classification, C-L-A-S-S-I, classification of matter. So what is matter? So matter, anything that has mass and that occupies a space is called matter. So pretty much everything you see around is called matter. So anything that has mass, if you put in the balance, it will show the number, and it occupies the space is called the matter. So anything you see around is a matter. Yeah. So there is nothing here that is not a matter. Make sense? Good. So how many kind of matter are there? There are 3 kinds of matter: solid, liquid, and gas. Liquid and solid, liquid and gas, right? Solid, liquid, and gas. So everything in this room is a solid. We drink whatever is that is the liquid, and something the gas is the flies here, like the carbon dioxide, air, water vapor, they are gas, right? So the matter are divided into three classes. They are solid, liquid, and gas. So another way of classification of the matter, so kind of the states, based on states. State means there are 3 states: solid state, liquid state, gas state. So we classify the material based on state is 3 kinds: solid state, liquid state, and gaseous state, right? So if you give the example, ice is a solid, right? Ice is solid. And liquid is water, so water. And the gas is like the water vapor or any gas, water vapor. So water vapor. So these are 3 states, right? So water can be found in 3 states: solid, liquid, and gas. But anything you see like in this room is pretty much solid. So if you have a water bottle and inside the bag, and what is there is a liquid, yeah? And the gas is the air around us, the carbon dioxide, the oxygen gas in the hospital, so everything, and the water you boil and get the vapor, they are gases, yeah? Make sense? Good. Now, classify according to the composition. So this is the according to state. So also we can classify the matter based on states. Based on composition. So let's say this is a cup here, and you put the iron pieces. So iron pieces. So this is called the element. So very pure. See, here is only iron. Iron pieces. Iron. So anything you see in the periodic table is called the element. Yeah. So that's a pure state. So so iron. So this is the element. So if you mix 2 things here, let's say these are iron pieces and they are copper turnings. So you are mixing. This is copper, COPP, copper, and these are irons. Iron. So you are mixing the iron. So this is a mixer. So if you are mixing 2 things in the same place, this is called the mixer, right? Iron and copper, water and stone, sand and salt. So you are just mixing there 2 things together, right? And then this is called the mixer. So this is called the element. Only one thing, pure, like what you see in the periodic table. Yeah. And then another one is compound. 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 So Compound. What is compound? Take 2 or 3 elements in the periodic table and combine together. So if you look at the periodic table, there is carbon. And if you leave the periodic table there, there is oxygen. And if you combine carbon and oxygen, they sit like this. So one carbon sits with the 2 oxygen atoms together. So this is called the compound. Make sense? So take any 2 elements in the periodic table here and just try to combine chemically, not mixing. So for example, combining means that, so let's say you have a hydrogen in this test tube, you have a hydrogen here and you have some oxygen here. So this is just a mixture. You see, these molecules are the oxygen here and these molecules are the hydrogen. Hydrogen and oxygen molecules are just mixed. They are doing nothing, right? They are just sitting there and just mixing, right? But if you bond it, so put a matchstick here, bond it. When you bond it, hydrogen will just explode and it gives water, H2O. So this is the compound. When 2 elements are combined chemically, and this is called the compound. Make sense? When 2 or more elements in this periodic table are combined chemically, we call compound. So pretty much in chemistry, we talk about the element in compound. Yeah. So if we talk about the these things in the periodic table, they are called. We are studying about the element. And if 2 elements or 3 elements are combined together chemically, they are called the compound. Yeah. So we'll talk about these things. Good. Now I'm in the slide number 5. So let's talk about some properties of solid, liquid, and gas. Properties of solid, liquid, and gas. So properties of solid, liquid, and gas. Solid, liquid, and gas. Liquid and gas. Yes. So solid is like they have the definite shape. So this is like a duster, like a cube, right? This is a definite shape. So solid has definite shape, and the molecules or atom of the solid are tightly bound, so these molecules don't move from each other. Make sense? So if they don't move each other, they have the lowest kinetic energy because they are not moving. So this is the solid. Solid has definite shape, right? And the molecules are tightly bound together. They are not moving, so they have the very small kinetic energy. They are not moving. Yeah. So this is solid. And this has definite volume. You can measure the length, you can measure the breadth, and you can measure the height, and you multiply length, breadth, and height, and you get the volume, right? So definite shape, definite volume, very tightly bound particles. The particles are not moving, so they have the least kinetic energy. Yeah. So kinetic energy sometimes is called the thermal energy. So I am moving here, so I have a more kinetic energy. So if you are moving, you have more kinetic energy. But if you are sitting, you have a least kinetic energy. Yeah. So the particle of the solid are tightly bound. So this is the one particle, this is another particle. So they are just tightly attracting together. So they are not free to move. So they have the least kinetic energy. Make sense? Good. So another one is liquid. So in the liquid has no definite shape. So if you let's say you have 1 liter water. If you put the water here, it looks like the bottle, right? But if you have a plate like this, and if you put that 1 liter water in plate, it looks like the plate, right? So the liquid doesn't have definite shape. Make sense? So whatever you put in, it takes the shape of that one. If you put the water in the bottle, it looks like the bottle. If you put the water in the plate, it looks like the plate. So the liquid takes the shape of the container. Yeah? Shape of the container. But it has a volume. It has a definite volume. Either you put here, it is 1 liter. Either you put here, it is still a 1 liter. So liquid has definite volume, right? And the molecule of the water are moving. So the molecule of the water here are moving. So if you pour somewhere, some of the molecule can go outside. If you heat here, some of the molecule fly away. So the molecule are moving. So the kinetic energy of the liquid is more. So they are moving. So in this solid, atoms, molecule are not moving. They are moving, but they're vibrating with a very, very small speed. But in liquid, they are vibrating or they are moving with a more speed. Yeah. So liquid has more kinetic energy in the molecule. Now, how about the gas? So gas doesn't have a shape. So gas doesn't have shape. So in the gas, they don't have a shape. So if you put in the cylinder, it looks like cylinder. If you put in the balloon, the gas looks like the balloon. So the gas doesn't have definite shape. Yeah, and also gas doesn't have a definite volume. So if you have a gas, so put the gas in the big cylinder like this. Some molecule are here, some molecule are here, some molecule are here, some molecule are here. So maybe you say, okay, this is a 10-liter cylinder. So this is the 10. So take this gas and put in a compression, a very small space like this. So it may have a let's say 1 liter volume. You see that? So same amount of gas can occupy different amount of volume, right? So if you put a 1 gram carbon dioxide gas in a big cylinder like this, it occupies 10 liter. If you put the same amount of the gas, carbon dioxide gas, in a very small cylinder, it occupies a small amount of the volume. So gas doesn't have the definite volume. Yeah. So it just takes the different volume according to its the container's size. And then kinetic energy. So in the solid, molecular tightly bound like this, very tightly bound like this, molecular tightly bound like this, so they don't move, very small kinetic energy. But in liquid, the molecule are moving, they are far away, so more kinetic energy. But if it is a gas, the molecule are even moving very fast, they are moving very fast, right? So kinetic energy of the gas is very high. Yeah, make sense? Good. So just to review the slide and this is fine. Now, this one. Now let's talk about this slide number 6. In slide number 6, I have a mixture. So the mixture is two kinds. So let's say you mix the this is water. So this is water. This is water. Now put a little bit salt here. Salt. Put salt and stir it. Can you see salt and water individually? You can't see salt and water individually because it is already dissolved. And you look here or you look here. Everywhere it looks the same. Yeah. So this kind of thing is called the homogeneous mixture. You can't see the component of the mixture individually. They are already so well mixed that you cannot differentiate with your eyes. So everything looks the same. So that is called a homogeneous mixture. So you mix water and salt here, and you stir it. Now you want to try to find the salt here. You can't see the salt. You want to try to find the water. You can't find. So both are mixed so well that you can't differentiate where is salt and where is the water. Yeah. So this is called a homogeneous mixture. Now, a homogeneous mixture consists of two or more substances in the same phase, meaning that everything looks like the liquid here. Yeah. Phase means whether liquid, gas, or solid. Yeah. Now, so uniform composition. So either you put salt water or sugar water, and you just stir it. Everything looks the same, meaning that uniform composition. Yeah. Uniform composition. Now, heterogeneous mixture. Now, take some water here. The water. This is water. This is water. Now, put some oil in this water and stir it. So this is oil. So you clearly see two phases here. So this is a water phase. This is a oil phase. So if you put water and oil together in the kitchen and then try to mix it, oil sit like this after a while and water sit like this, and you can clearly see there are oil drops here and there is a water here, right? So this is a two phase. So this kind of mixture is called heterogeneous mixture. You can clearly see two phases with your eyes. Make sense? So this is the heterogeneous mixture. Now, how about this one? So you have water here. Now put some stone here. Can you clearly see water and stone here? Yes. With our eyes, we can see water here, and also we can see the stone here. So this is also heterogeneous mixture. So if you can see two or more things in the mixture with your eyes, that is called a heterogeneous mixture. And if you cannot see everything looks same in that mixture, that's the single phase, that is called the homogeneous mixture. Make sense? So water and liquid, if you mix, if you mix the oil and water, you can clearly see two phases, oil one side and water one side, that's heterogeneous. Yeah? Good. So if you see two or more phases in the mixer, that is called heterogeneous mixer. But if you see only one phase in the mixer, that is called the homogeneous mixer. Yeah? Good. Now, what else here? A pure substance. Now I am in the slide number 7. Pure substance. What is pure substance? So, pure substance. Pure substance. Pure substance. So what is pure substance? Pure substance is that substance that has a unique physical property. So if you take a water, only water, take 100% water, there is nothing, only water, there is only water, this is only water, this H2O is water, yeah? So this is water. If you try to boil this water, it boils at 100 degrees centigrade. It boils at 100 degrees centigrade. There is nothing in the universe that boils at 100 degrees centigrade. So this is a pure water. Make sense? So if something has a very unique property, that is a pure substance. Yeah. So a pure substance has a well-defined physical and chemical property. Well-defined meaning that you are trying to study the physical property of water, and you go. So somebody give you a liquid, and somebody asks you what this liquid can be. So your job as a chemist is to find what this is. Right now, you start to boil it. You start to heat it, and it boils at 100 degrees centigrade. So if it boils at 100 degrees centigrade, it is 100% pure water. There is nothing in the universe that boils at 100 degrees centigrade at a room. Yeah? So it has a very, very unique physical and unique chemical property. Yeah? So how about this one? So if you have a water here, and then somebody put some salt here, and then you try to boil it, it may boil at 120 degrees centigrade. It's not a pure water. So if it were a pure water, it would boil at 100 degrees centigrade. But if here is somebody give you a liquid, and then you start to boil it, and here he claimed that it is a water, and you start to boil it, and it only boils at 120 degrees centigrade, right? So definitely that is not water. Somebody mixed something there. So pure substance, if it is a pure substance, that is a unique physical property or a unique chemical property. Make sense? So like that. Now, so pure substance can have can be element or compound. Water is a compound. Water is a compound. So if it boils at 100 degrees centigrade, it is a pure water. But if it doesn't, if it boils below 100 degrees centigrade or above 100 degrees centigrade, that's not a pure water. Yeah? Good. Now, what is element? Now I'm in the 8th slide. What is element? So anything that you see in the periodic table are called element. If something is not there, that is not element. Make sense? So I might ask some question like this. Okay, which one is not element? Hydrogen, I put hydrogen, iron, copper, and water. Copper and water. So I might ask you, which one is not an element here? So look the periodic table. It is in periodic table. This is an element. Look the periodic table. It is in that. So this is element. So this is also element. But this is not element. H2O is not in periodic table. Try to look the H2O in the periodic table. There is not that H2O, right? So H2O is not element. So what is there in the periodic table is element, and something there is not the element. Make sense? So what is a compound here? So this is in periodic table. So this is element. This is in periodic table, element. This is in periodic table, element. But two elements of the periodic table are combined here. Two hydrogen and one oxygen. So this is a compound. Make sense? So any two or more thing of this periodic table are chemically combined and written like that in the formula like this, that is called a compound. Make sense? Good. So element, this element cannot be cut. So if some reason you want, I want to cut this hydrogen, you never be able to cut this element. You cannot break it. You cannot break it. You cannot break it. But if you water, you can easily break it. So how do you break water? So put water in a beaker here and put some iron rod here and supply the electricity. Supply the electricity plus minus here. You can easily see hydrogen, this water molecule breaking and giving hydrogen and oxygen gas like this. You see, water you can cut it. So compound can be broken into two or more smaller elements. But these elements Whatever you see in this periodic table cannot be broken into smaller part. Make sense? But compound you can easily break into two or three. So if you have a sodium chloride, so let's say this is a table salt, and HCl is a table salt. So sodium chloride, if you want to find the sodium and chlorine from this compound, you can easily do. So what you do is, so put some water here, and then put iron or copper rod here, and put the sodium chlorides here in the water, and then supply the electricity, and then you will see at the one side you will see the sodium deposited, and minus side, plus side is sodium, and then in another side you will see the chlorine deposited. So you can easily break the compound into two or more parts by using certain techniques. Yeah. So this is called electrolysis. What I just taught here is electrolysis. You use the electricity to cut this into two parts, sodium and chlorine. Make sense? Good. So compound can be broken into two or more parts by certain technique, but element cannot be broken into two or more parts, no matter what you do. Make sense? Good. Now, still I have a couple of minutes, so let's talk it here. I am in the slide number 9. Slide number 9. So in the slide number 9, there is a qualitative and quantitative. What do you mean by qualitative observation, and what do you mean by quantitative observation? Think about this board. How does this board look like? White. So white meaning that's a qualitative observation. Yeah. So take the tape and measure it. How long it is? Maybe this is maybe 10 feet. So maybe this is 10 feet long. So this is a quantitative observation. So if you see the number and you have the unit there, this is called the quantitative observation. But if you see and look the color or a texture or something like this, that's called the qualitative observation. Make sense? So put some, this is a balance here, I put there. So this is a balance and you can read number here. So put some in this weighing board, you can put some copper. So what is the color of the copper sulfate? Blue. So you look with your eyes, you look the blue. So that means that's a qualitative observation. Yeah. So the balance will show the number here. So 5.00 grams. So this is quantitative observation. So quantitative observation has a number with the unit. Qualitative observation has just the, how does it look like? Oh, it looks like blue. So that's a qualitative. How does it look like? It's a liquid. It's qualitative. How does it look like? Gas or solid? That's a qualitative. Yeah. But how much? 5 grams. What is the length? That's a 10 feet. So if you have a number in unit, that's a quantitative observation. If you have just the color or state you are looking, that's called the qualitative. Make sense? Qualitative is color or texture. Quantitative is number with the unit. Yeah. Makes sense. Good. Now, I think okay. So let's do number 10 slide and. So chemical and physical change. So let's say you have a milk here. So you have a milk and you put it with some bacteria and you found the yogurt. So this is chemical change. It's a chemical. Can you convert yogurt to milk? It's impossible, right? Yogurt cannot be converted to milk, right? So this is kind of one-way conversion. So this kind of thing is called chemical change. Chemical change. Completely new form is formed from one form. So you convert it, and a completely new form is new kind of material is formed, and you cannot change this back to this. This kind of change is called the chemical change. Milk can be converted to yogurt, but yogurt cannot be converted to milk, right? So this is a chemical change. But how about this one? You have ice here. Ice piece, and then you heat this ice and you get the liquid water here. Liquid water. So this is ice, this is water. So you heat the ice, you get the water. Now you freeze the water and you get the ice. So this kind of change is called the physical change. You can just convert that. Yeah. So ice is also water, and what liquid water is also water. The same form, very pure, the same chemical composition. But if you took the chemical composition of milk and chemical composition of yogurt is completely different. Yeah. So in this course, whatever we study is the chemical change. We don't study the physical change here. Yeah. So in future, in this course, what we will be studying is everything is a physical change. So it's a one-way conversion. So I put the sodium and I put the chlorine, and when the sodium and chlorine are put together, completely new thing is formed, sodium chloride. So this is a metal, this is a non-metal, and when I put metal and non-metal are reacted, I got the salt and I can eat it. If I eat sodium, I die. If I breathe with the chlorine, I die. But if I eat the sodium chloride, I feel so good. See that? It's a completely new thing is formed. Make sense? So this kind of thing is called the chemical change, and this ice converted to water, water converted to ice, water converted to liquid, water liquid converted to gas, water vapor, and water vapor converted to liquid water. These kind of are called the physical change. But here, you simply cannot convert this one. You can convert this one, but you simply cannot. I already told you, if it is electrolysis, you can break it, but electrolysis is something fancy things, right? So only very highly experienced people can do, but anybody can convert ice to water, water to ice, right? So this kind of thing are called physical change, and this kind of thing conversion where completely new form is called new thing is called the chemical change. Make sense? Good. What else? So I think we are done today. So there was a small one slide I will talk in next class. Yeah. Good thing. Thank you very much, everyone. So I only post the homework on Saturday, so you can do the homework next week. Yeah. Thank you, everyone.